Pretty good. Okay, let's see what we got going on without your calculator. Yes?
314 is the same rate of Benny's, correct?
Yes. Yep. And you know, that reminds me, I saw that like little lecture guide. I thought about, now what would I tell students to get ready for the test tomorrow? And what I would tell you guys to do is go look at that sheet that's at the beginning of the, like this one, but analogous to Unit 3. And I almost did that for today, but I ran out of time. Did I tell you that our daughter had her wisdom teeth removed? Yeah.
Uh-huh.
So that's kind of, it went well. She had all 4 removed. So this is what I'm looking for. If I was going to tell anybody like what's going to be on the test, I'd be like, this is your roadmap. Okay? And if any of these look kind of strange and you don't know what they are, then probably go look them up. Okay? So it's my word of wisdom. Thank you. Okay. So we are going to revisit the atom. Now, it's like an awesome story of the atom. Scientists are great about piggybacking on what previous scientists knew. So Dalton actually kind of revisited the idea that all matter is made up of atoms. He didn't invent it, but he came up with Dalton's atomic theory in 1803. And so that little red thing is an atom. Okay. So Thomson further built on that, and you can kind of see the yellow model. It's the plum pudding model, and actually Thomson said, all right, but actually atoms have positive and negativeness to them. Okay, still doesn't look like the modern day atom that we know, does it? Then Rutherford, you can kind of see the light purple and the dark purple. The dark purple is the center of the atom, of course we call the nucleus, and the light purple is where the electron's going to be. Okay, so Rutherford had that idea, electron outside, you're giving the atom volume, and the nucleus inside. Well, then Bohr piggybacked on that, and now you see these little orbs here are electrons. Okay, so this is actually, and one of the things you probably already ran into before is that we can actually say electrons have different energies. And that's what Bohr said. He focused kind of on the hydrogen atom, and he said, well, that electron around a hydrogen atom can have different energies. So that's what that is. And then we come up with Schrodinger, and actually that's the last of the models. So Schrodinger enhanced Bohr's model, and he said that actually, I don't know if this kind of looks like it to you. Does this look like the sun and the planets orbiting the sun? Okay, so that's kind of the solar system of the electrons orbiting the nucleus. That's not how it works. Instead, actually, and it kind of makes me itchy if I think about it too much, the electrons are kind of, they're in a cloud, but it's uncertain actually as to their specific location, where the electrons are located. We know the general region, we're going to call that an orbital, okay, where the electrons are and kind of how much energy they have. I was listening to, because I'm on news blackout, I was listening to Star Talk radio with Neil deGrasse Tyson, and he was talking about, they were talking about Star Trek, and as the science on Star Trek, you know, like the series, is it real? And they were talking about, you know, the whole, you get in the transporter and they beam you over. Okay? Now that relies on basically being able to map all of your atoms and then recreate them over at the other transporter site. And then actually there's something coming up called Heisenberg's uncertainty principle. That question mark there reminds me of Heisenberg's uncertainty principle. Where is an electron and exactly what spin does it have? We can't know exactly, and its energy all at the same time. So anyway, they said that this morning on the I thought that was pretty cool. Okay, so we're going to kind of just take a quick look. This actually is Thomson's plum pudding model, where he said that we kind of have, he didn't have the idea of the nucleus, the protons and neutrons in the nucleus. He said the electrons and the protons are kind of all just schmoozed. Now this green orb kind of talks you through the atom helium, which we know helium is atomic number 2, so it has 2 protons. So Thomson says it has 2 pluses and 2 minuses. And then Thomson here kind of talks you through, if it loses 1 electron, okay, it becomes a +1 ion, and if it loses 2 electrons, it becomes a +2 ion, which is a really strange thought if you think of that helium atom letting go of both of its electrons. It's kind of strange. And then this one kind of steps it up to at least the Rutherford model. The fact that in the nucleus are the protons and the neutrons, and then outside the nucleus in a cloud are the electrons. Okay, so then after Rutherford and Bohr and Schrodinger all had this kind of enhanced on a little bit about the electrons. So speaking of a little bit about the electrons, electrons can change energy levels. And in this class, if I'm standing up here and I go like this is low energy, and if I go up here, this is high energy. So kind of along the y-axis, think of basically an energy, increasing energy as you go up. The other thing about increasing energy as you go up, in my little model up here, is this is the nucleus of the atom, okay? So as I go up, I get more energy, and I'm farther away from the nucleus. So one of the things Bohr noticed, with his solar system model of the electrons orbiting the nucleus, which isn't really how it is, but he said electrons exist here at this energy, or electrons exist here at this energy, or electrons, if there's room, can exist here near the nucleus. Now I've just shown 3 different locations with regard to where the electron is. And actually, if I put an E over here, my imaginary E, I've just showed 3 different energy amounts for that electron too. And so finding homes for electrons. Now again, you guys, if you've taken general chemistry in high school, you've probably done something like this. So just bear with me because I kind of put a little extra twist on what we call electron configuration. We'll hit that hard on Friday. But what this is just kind of a simple look at how Bohr would put the electrons. So for instance, we pick on carbon a lot. I'll pick on carbon here. Carbon's atomic number 6, 6 protons. And then here's how the 6 electrons are. There's 1 in this energy level, n is equal to 1, and there are 4 in this energy level, n is equal to 2. Okay, so 2 plus 4 is 6. So those are how the 6 electrons are around that carbon atom. Okay. And this one doesn't work. My animations don't work this semester. But if I could animate it, okay, obviously you guys are probably on track that this is the nucleus, okay, and then these are the electrons. And what the video does is say it kind of looks like I have those electrons orbiting the positively charged nucleus. There is an electrostatic potential. It's not gravity that holds those electrons in place. And they aren't on a path that we know. Like the planets, we know where the path is. Okay. This is more like than Schrodinger's model. It kind of looks like a little Christmas sort of thing going on. Oh my gosh, my Sirius radio, it changed one station I usually listen to a Christmas station. Oh, no. So anyway, because I'm on a news blackout. So this actually is kind of showing the electron cloud. Those little dots are where the electron can be. All right. So again, as I stand up here and my foot is the nucleus, electron can be here in a cloud, here in a cloud, or here in a cloud. Notice what it can't be is kind of in between. We call those 3 discrete states, 1, 2, 3. And there's more than just that, but okay. So we say the location and the energy associated with an electron is quantized. Okay, it's not on a continuum, it's quantized. So on your Unit 4, I know you haven't had your Unit 3 exam, but looking ahead to your last unit exam in here, I'll have to have a vocab section, and this is a favorite vocab word. Quantized, what does it mean? It means here, or here, or here, but not in between. So kind of as an example of that, I have, and I noticed the other day when I was looking at my slides, look how flat top that guy's hair is. I'm like, dude, it looks like, and then I went into the graphic and I'm like, am I missing part of the graphic? No, his hair is just flat like that. Okay. But do you see where both chemists, and drawn to scale, can you imagine if we were climbing steps that were about that high? Climb another step? I know. So it's not drawn to scale. But the idea is that they are both on the same elevation, okay? But do you see where this one on the left, he can only be at this elevation, this elevation, this elevation. He only has 1, 2, 3, 4, 5. 5 specific places he can be. And this guy over here, man, he can be anywhere, an infinite number of positions. Okay, so this is quantized. His elevation is quantized over there. Okay. So I go back over here. My foot is the nucleus with the protons and neutrons, and then my hand is actually showing you different energy levels. So if you have your entire set of possible electrons, like for carbon, we said there's 6 electrons. If we have all 6 electrons that are kind of hugging as close to the nucleus as possible with the lowest amount of energy as possible, we call those set of electrons in their ground state. Sometimes I call this couch potato state. It's like the easiest. Notice it's lower energy and it's got the most stability. And actually, as we talk about how electrons are hanging out, we're going to focus on ground state, what we say configurations. Well, the opposite of ground state would be excited state. Oops, sorry. Okay, so an excited state obviously is, for instance, if there was room at this energy level for that electron to be hanging out, at that location and that energy, if it gets zapped with a certain amount of energy, it can actually then be promoted to a higher energy level. Okay, we say then that electron is farther from the nucleus, has more energy, that electron is in an excited state. It's an excited state and it's kind of an unstable situation, kind of just itching to fall back down. Of course, the cool thing, and you can read in your textbook in this chapter how this works, but the cool thing about electrons that are excited, guess what? When they fall back down, they emit a certain amount of energy as they fall back down. So instead of zapping them, it goes zzz, okay? And that amount of energy is characteristic of the jump that they jumped. So cool. That is so cool. Okay. So remember back in Schrodinger's model where we had kind of the itchy looking sort of zzz, where are the electrons? Well, the electrons are in this cloud outside the nucleus. That kind of outside, that cloud outside the nucleus, we can kind of think of as an electron orbital. Where is the electron? Well, it's in its orbital. Okay. But even in that just kind of glance at Schrodinger's model of an atom, if you go back to it, you'll kind of see where the itchy sort of, it kind of peters out as you get farther. So it's like a probability thing. Okay, the distribution is a probability thing. Okay. Now we're kind of segueing, that was kind of the background information of the structure of an atom. And it's all about the electrons, kind of the last discoveries about the atom. And now we're going to continue to focus on electrons, the energies that electrons have, and ultimately being able to designate both with regard to location, but more importantly with regard to energy that an electron has. And we are going to find homes for electrons in orbitals, okay? And let me go ahead and show you a little bit, kind of get you thinking how this is going to look. Anytime you see a box, here's my box. Sometimes they get kind of ugly. That is an orbital. The other important thing about here is it says we can put 2 electrons in any given box, okay, but they have to have opposite spins. Here's what that looks like. We use arrows to represent electrons. So here's my first of 2 electrons, and I'm going to use an arrow pointing up, and we're going to talk more about this on Friday. If I'm going to max out that orbital with a second electron to show the opposite spin, I'm going to do an arrow. I'm going to be pointing down. That's an orbital with 2 electrons with opposite spins. The arrows are the electrons, and the box is the orbital. Okay. Very good. So orbitals, which are boxes, are arranged in what we call subshells. Okay, and I'm going to revisit that. Let me go ahead and show you. You've run into this before probably if you played around with electron configurations. The subshells actually have names, and actually names as in letters. So we have an S-type subshell, I bet you've heard of that, a P-type, a D-type, and an F-type. Those are the types of subshells that we need to work with. I'm going to go ahead and throw something else at you because I'm kind of thinking down the road. Underneath the S, P, D, and F, I'm going to put a number that actually you're going to see on the later slide. Those letters correspond to 0, 1, 2, and 3, respectively. So S is 0, P is 1, D is 2, F is 3. A lot of times students have come into this class and they're already familiar with the S, P, D, and F. Like, I got it. But I want you also to know that they have what we call L values of 0, 1, 2, and 3. Okay. Those are subshells. Subshells of orbitals are found in different energy levels. Oh, I put something. Did you guys catch that at the end? I put an L here. I put an L next to this. L is the subshell. I'm going to put a variable N for the energy levels. And just for kicks, I'm going to revisit that thing up here. For my orbitals, I'm going to put an M sub L. Those are my orbitals. So I think I'm going to start with the last one, the N's, and I am going to make something over here. This is going to be increasing energy. And so this is going to be my nucleus. So not only do we have a proximity to the nucleus thing, but we also have an energy thing going on. So I'm going to go ahead and put N is equal to 1. That's a principal energy level. N is equal to 2. N is equal to 3. And N is equal to 4. So you kind of get that idea. Okay. I mentioned Heisenberg's uncertainty principle with whole Star Trek thing. I don't know if you followed that. Hopefully you did. But according to, and I've looked this up a little bit, this uncertainty principle works only for very small things. Okay, so all very small things. It just works very well for electrons. So specifically, we can't pin an electron down with regard to location and energy. We just can't ever do it. So thus the transporter thing doesn't work. And that's why Bones would never allow himself to be transported. So if you're not a Star Trek fan, I'm sorry. Okay. Of course, Heisenberg made himself, the name became commonplace when Breaking Bad was popular, so he was an evil person. Okay. So the goal of, that's a lot of background. Now, the goal of what you guys are going to be tasked with is actually to ultimately, I'll say pin down. I just said you can't pin down, but you can kind of get to a general location and a specific energy that an electron has, okay? And so for each electron, we're going to give them a zip code. We're going to give them a zip code with regard to N, with regard to L, with regard to M sub L, the things I told you a minute ago, and the last zip code we're going to talk about on Friday is their spin. So there's going to be 4 quantities to give a zip code, okay? So N. N is like N is like, I think I say maybe the country or something. N is very vague, okay? Then we get a little more specific. Within N, we have these L's. I'm going to actually add to this little energy diagram over here. I'm going to add some little subshells under those principal energy levels N in just a minute. So we get a little more specific L's. Remember, L's are our S, P, D, and F. 0, 1, 2, and 3 respectively. And then we get into basically which little box. Remember I told you to, with regard to orbitals, I said put a box, that's your M sub L. And then the last quantum number to complete the description of what an electron's all about is what we call the spin number, or the M sub S. Guess what? There's only 2 values of M sub S. Okay, what does that stand for? You know, up arrow, down arrow. Okay, we're going to put a +1/2, a -1/2. That's it. So I guess it wasn't country. I went a little more local. So if you wanted to find somebody's house that didn't live in the area, you'd ask them what state they lived in. Narrow it down, you'd ask them their city. Narrow it down, you'd ask them what street in that city. To narrow it down, you'd ask for which address on that street, in that city, in that state. Okay, so it just kind of narrows down. I like it. So there are rules. There are rules with regard to your zip code. Now, the N's that I put up here, that's your principal energy level. And actually, I've only drawn up to N is equal to 4. N could go to infinity. Does it go to infinity? Not if you're finding homes for electrons that are in their ground state. Okay? But you can excite them up to infinity. Right? So they're whole numbers from 1 to infinity. And like I've kind of drawn here, what this is saying is the higher the N, then the higher the energy and the farther away it is from the nucleus. That works. How hard could that be? And again, that's kind of your state. So I think I'll go ahead and over here, you may not need it, but I'm going to say rules. Let's see if this helps. Actually, these are the quantum rules. The quantum numbers, quantum mechanics, actually it's a takeout of physics, and quantum mechanics, as I understand it from years ago, would allow you to walk through a wall. That's quantum mechanics. So anyway, N is equal to integers 1, 2, 3, 4, all the way up to, all right. Oops. Now, this is going to make more sense. Yeah, we did valence electrons. Yeah, we did electron configurations. Didn't we do? No, we didn't do that. I'm thinking of my other group. Okay. But we did talk about periods. We talked about groups and periods. And for instance, strontium is in period 5. And so the valence electrons for strontium will be N is equal to 5. Skip on over to chlorine. Chlorine is in period 3. So when I go to talk about the electrons around a chlorine atom, there'll be 17 of them. And the valence electrons are going to be in N is equal to 3. So actually, we're going to come revisit that. Some electrons are special. They're called valence electrons. They're all special. Okay. So then we get to the L's. Remember I told you the L's are the S, the P, the D, and the F that you may have learned before. Maybe, maybe not. But L's have these rules. L's are also integers. They start at 0 instead of 1. And they go 1, 2, 3. But they have a cap. They can only go up to N is equal to, N minus 1. That's how big they can go up to. Okay. And that's what we call the orbital type. S, P, D, F. And I'm going to put 0, 1, 2, 3. Oops. So here we go. I'm going to add to this. Well, maybe not. Yeah, let me go ahead and add to this first. Okay. So do you buy this? When N is equal to 1, we can have L values of 0 all the way up to 1 minus 1. 1 minus 1 is 0. So check this out. You only have one L value. You can only have L is equal to 0. That makes sense because of the rules. And I told you that that corresponds to an S. All right, let's bump it up. N is equal to 2. 2 minus 1 is 1. So here we have 0 and 1. So here we have N is equal to 2, L is equal to 0, and L is equal to 1. That's it. Of course, that corresponds to an S, and that corresponds to a P. Like, why didn't they just stick with letters instead of numbers? But that's exactly what we're talking about. Let's do all the way up to 4. When N is equal to 3, I got 3 minus 1 is 2, so I have to stop here. So I have 0, 1, and 2. So I have L is equal to 0, L is equal to 1, L is equal to 2. There's my S, my P, and my D. Now, if you're like, well, that's the way I learned it, well, then you're learning it again, maybe kind of with a different spin to it. I actually run into troubles with people knowing this stuff. Okay, last one. N is equal to 4, so we have 4 minus 1, which is 3, so it kind of stops here. So I have the L values of 0, 1, 2, and 3. And that corresponds to, of course, S, P, D, and now we get the famous F. So that's kind of how that goes. All right. So S, P, D, and F. S, P, D, and F. You're like, well, you already told me that. Well, now I'm officially telling you on a slide. So the L value of S is 0. The L value of P is 1. The L value of D is 2. The L value of F is 3. Do I need to know this? Yes. So now there are other L values because they go all the way up to N minus 1. And if N can possibly be infinity, good heavens, right? So we have a whole bunch of other different subshell types. Okay. Do we need them? No, because I told you we are actually going to find electrons as they are in orbitals about their nucleus and they're hanging out their ground state. So I've gone ahead and included when L is equal to 4, actually that would be a G-type orbital for excited electrons. When L is equal to 5, an H-type subshell, I guess I should say, G-type subshell and H-type subshell for excited electrons. All right. The highest orbital type, and that kind of says right here, highest orbital type we need to worry about is L is equal to 3, which corresponds to an F. Okay, an F-type subshell with those orbitals on that subshell. We don't need the G or the H or the I, the J or the K. Okay. All right. So for each subshell, and I've kind of drawn them here, I sometimes call this the onion, or this is the center of the onion. We have these layers of the onion. I don't know. So each subshell actually then has an orbital or a set of orbitals. And I'll kind of show you what I mean by that. I'm running out of room, but over here, and it must be coming up on a slide. Over here, I'm going to go ahead and put subshell type. And I'm going to go ahead and put S, P, D, and F. In parentheses, I'll put 0, 1, 2, and 3. And I'm going to go ahead and next to them put the number of boxes, that's boxes in orbital, that is in that subshell type. So S has 1 box, and it's all about oddsies. Okay, the next odd number from 1 is 3, and a P-type subshell has 3 boxes. A D-type subshell has 5. I'm going to run out of room. And an F-type has 7. Sometimes my boxes get sloppy. 3, 4, 5, 6, 7. Cool. So S, 1 box, P, 3 boxes, D 5 boxes, and F 7 boxes. And remember those boxes are the orbitals. And we said that orbitals can hold 2 electrons. I mentioned this because then now we can actually start filling in our onion. So I'm going to go ahead and call this guy. I'm going to call this subshell 1 because it's energy level 1. And I'm going to call it S because it's an S type. And I'm going to go ahead and put 1 box. Here, I'm going to call this 2S. And I'm going to put 1 box. And here, I'm going to call this 2P. And how many boxes do I put here? Since it's a P type. Yep. Put 3 boxes. And then I'm going to go up to n is equal to 3. I'm going to put 3S, 1 box. 3P, 3 boxes. And then 3D, how many boxes for that one? 5. Cool. And then I'm going to go up to n is equal to 4. And I'm going to put 4S, 1 box. And I'll put 4P, 3 boxes. I'll put 4D, 5 boxes. And I'm going to put 5F. How many boxes? Oh, sorry, 4F. 4F. How many boxes? 7. Very good. So not to necessarily get ahead of ourselves, but I'll show you what we're going to do, I think, on Friday. I think we'll get to this. The 6 electrons around a carbon atom, here I go. 1, 2, 3, 4, oops, opposite spins, 5, and this is a little bit different. I'm going to go ahead and spread out if I can. 5, 6. So those arrows are electrons, and I'm kind of showing you how they're hanging out around a neutral carbon atom. I've kind of showed you what we call this is the off-bow method, kind of building up. Now I did all that, and actually this is a good example to say what this slide is all about. This slide talks about degenerate orbitals, and I'm going to pick on right here. Do you see these 3 guys right here? Do they look like they're at the same energy? Yeah. So these are actually 3 degenerate, it sounds like a bad thing, but it's not, orbitals of 2p. Okay, it just means they're equal energy. Seems like I did a lot just for this slide. So one of the things you're going to have to be able to maneuver around is to kind of, it's almost like a type of mapping. You're going to have to map the L is equal to 0 to an S type. You're like, why? Because I said so. You're going to have to map the L is equal to 1 as a P type, and the L is equal to 2 to a D type. Okay, that's your L values mapped to maybe something you're already a little bit familiar with. Okay? All right. What type of orbitals are allowed at each energy level? What type of orbitals? Now, when they say what type of orbitals, I'm talking about kind of subshell types. So actually, this question was answered when I kind of did this diagram here. Okay? So like, for instance, when n is equal to 3, what is allowed for L? Well, we look at the rule for L, and L is 0 up to n minus 1. And if n is equal to 3, let's see, 3 minus 1 is 2. So, you know, that's why I had L values of 0, 1, and 2. Okay? It's like a little math game, kind of. So again, this is just kind of stepping through what I already did when I kind of drew this little kind of onion thing. When n is equal to 0, sorry, when n is equal to 1, there is no n is equal to 0. It's not an allowed state. When n is equal to 1, your possible values for L is just 0, and that's an S type. When n is equal to 2, you can have 0 and 1. That corresponds to S and P. So again, I kind of wanted to bring you along with this diagram while we went with this slide, these slides. I think it makes more sense. All right. So when n is equal to 3, we have values of 0, 1, and 2. And actually, on your homework and on your test, it's going to ask you questions like, could you have an L is equal to 4, excuse me, could you have an L is equal to 3 at n is equal to 3? And the answer is no, because it maxes out at n minus 1, which is 2. I feel like I'm almost talking in riddles, but that's how that works. When n is equal to 4, we have values of 0, 1, 2, and 3, which corresponds SP, D, and F. When n is equal to 5, which I ran out of room, okay, then we actually get our G-type subshell with G orbitals, okay, which, wow, according to this pattern would be what, 9? Okay? But in finding homes for electrons, even filling in all the elements like the period number 7, they're all filled in now. As long as those electrons are in their ground state, we won't need to go there. Okay? So this is just kind of another look at the allowed L values. Remember, L goes to your subshell type. Okay. So this says, and this actually I've already done on the diagram a little bit. This says, for instance, if we go all the way up to n is equal to 4, you have, 3 different allowed subshells. And notice I put them in order of going up, increasing energy. That's the way it works. Okay, here, the 2s has less energy than the 2p. 2p has more energy. So that's kind of how that works. Now, I'll tell you later. Because I need to I've put something up here that's going to be, it's not really a mistake, but it's actually going to have to be revisited when we talk about energies. In the meantime, let's talk about the third quantum number. And we'll save the fourth quantum number for Friday. But the third quantum number is the box itself. And this is kind of fun. This used to confuse me. Let's see if it can, not confuse you. So the rules of this quantum number is m sub L. It's called the magnetic quantum number. It has values. You can look at it 2 different ways. I kind of prefer this one, the 0, the plus or minus 1, the plus or minus 2, all the way up to the plus or minus L. Okay? Oops. Okay, so let's see. I think I can kind of squeeze it in. I'm going to circle that. I'm going to uncircle this. So, for instance, when L is equal to 0, it's 0 all the way up to plus or minus L, and L is 0. So guess what? It's just 0. So check this out. I'm going to, underneath this box right here, I'm going to write an m sub L value is equal to 0. So any S-type subshell has one box, and what's its m plus L value? 0. Okay? Any P-type subshell, the L value is equal to 1. So we have 0 plus or minus 1. We stop. Check this out. So I'm going to put this m sub L is equal to 0 here. Now, this one, I kind of go symmetrical. So I have 3 m sub L values, and I have 3 boxes. So my m sub L value can be 0, plus 1, and minus 1. So what I usually do is kind of put 0 here, and I go minus 1 here, and plus 1 there for my m sub L values. I know it's kind of small. And I could do that up here. So m sub L is 0 for this one. M sub L is minus 1, 0, and plus 1 there. Isn't that fun? Okay. So here, when D-type subshells, D orbitals, L is equal to 2. So we have 0, plus 1, minus 1, plus 2, minus 2, and end. So I got 5. 1, 2, 3, 4, 5. We got 5 boxes. So here we go. To me, it's like a visual thing. M plus L value of the D's, I'll go -2, -1, 0, +1, +2. That's it. Let's get on up to this guy right up here, F. So we have L's equal to 3. So we're going to go M sub the L value of 0, +1, -1, +2, -2, +3, -3, and we're done. So I got 7. So they look like this. And coincidentally, I have 7 boxes. It's not coincidental, right? So I'll go -3, -2, -1, 0, +1, +2, +3. We're done. That's it. So here's the deal then. For instance, do you see where, I wish I had another color up here, but I'm going to put a star next to this one, and it means for that electron. When I say we're going to have a zip code for an electron, here's what it goes. Usually, and I think this is right, usually for zip codes, you give the N, you give the L, you give the M sub L, and again, we're going to talk Friday about that last quantum number. So to give a zip code, you got to give that 4 pieces of information. So for this guy right here, do you guys buy this? That, let's see, the N is 2, the L is 1, the M sub L, I'm pointing to this one, it's -1. And again, we're going to talk about this M sub S, but all that is, it's pretty easy. We go +1/2 is an up arrow, and -1/2 is a down arrow. There's only 2 choices. So as I've written it, I'm liking +1/2. That's it. That is the set of quantum numbers that says where that electron is. Is that not cool or what? I love it. So I hope that was helpful. So how many different orbitals can be found in a particular subshell? Again, the rules are 0, ±1, your M sub L values. 0, ±1, ±2, all the way up to ±L. So it's just like I've drawn over here. Anytime you see an S-type subshell, of course S means L's equal to 0, so if you plug it in for your rules there, you can have 0 all the way up to ±0, which is just 1. And that's why I did an M sub L is equal to 0 under my 1 box in my S-type subshell. If you have a P-type subshell, whether that's N is equal to 2, N is equal to 3, N is equal to 4, etc., you're going to have 3 boxes for P-type subshell, and you can assign M sub L values for each of those boxes. They will be 0 and plus and -1. So that's why I went -1, 0, and +1, 3. That's it. And then the D-type, L is equal to 2. So you got 0, ±1, ±2. So that's actually 5 designations. And last but not least, that we have to concern ourselves, L is equal to 3. So then that's where you get the 7 different values for M sub L. 0, ±1, ±2, ±3, which gives you 7 orbitals. Phew. So the way your questions that we won't get to today, but we will on Friday, the way your questions will work are something like this. I could go over to, for instance, this guy right here. I said that this is actually the quantum state, okay? The N value, the L value, the M sub L value, and the M sub S value. Only values are +1/2 and -1/2 of this guy right here. But do you see where I couldn't make this, for instance, I couldn't make this 1, the L value. I can't have an L value of 2 here. Why? Because n is equal to 2 doesn't allow L is equal to 2. When n is equal to 2, the highest L value you can get is n minus 1. So that's the kind of questions you're going to run into. All right. The number of orbitals, those are boxes, that are found at any principal energy level, n, okay, can be found, okay, if you know the subshells in that n and you know the orbitals per subshell. You know, if you're a visual person, you can't bring notes to your Unit 4 exam, but you can recreate something on your Unit 4 exam if you wanted to. In fact, sometimes when I do the answer key for Unit 4, I'll just draw my little onion. And I'll be like, oh yeah, that's how that works. Okay? And I'll take a snapshot of this and push it out on Twitter. Okay, so for instance, if we focus just on n is equal to 3, and you're supposed to come up with how many orbitals? Orbitals are the boxes. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. That's it. You're done. Okay? You know, you can, I like the picture. I can also kind of maneuver my way around the numbers, but I like the picture. Because this is saying when n is equal to 3, then you can have possible L values of 0, 1, and 2 that correspond to S, P, and D respectively. And this is saying that in order to get 9, what I did is I took the 1 orbital in the S, plus the 3 orbitals in the P, plus the 5 orbitals in the D. I added them all up to get 9. That's all that is. I have a slide coming up to tell you a shortcut to this. If anybody ever asks you in a principal energy level, how many boxes do you have? It's just n squared. N squared. Let's check it out and see if I, so what's 4 squared?
16.
16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Isn't that fun? Okay, 2 squared is 4. 1, 2, 3, 4. Isn't that fun? Okay. So, this is kind of how far I wanted to get. That's good. This actually, the thing I don't like about this is it kind of inverts. You know how I've kind of drawn the energy going up? This is actually just inverted. So n is equal to 1. We have only one possible value of L. Okay, when n is equal to 2, we have 2 possible values of L, 0 and 1. And then the possible values of m sub L in the P, remember this is P, your m sub L values are plus 1, 0, and minus 1. Notice that I went minus 1, 0, and plus 1. It's the same diff. They're degenerate, okay, which means that, doesn't mean something bad, it just means they're interchangeable. Okay, yep. N is equal to 3, we have the S, the P, and the D. And you can see the M plus L values. N is equal to 4, we picked up the F. So that's S, P, D, and F for 1, 3, 5, and 7 different orbitals. Then over here, I have the N squared thing. Okay. If you want to quick and dirty, want to know the number of orbitals in any principal energy level N, you just have to raise it to the 2nd power. Isn't that cool? And then this one's a little bit different. It said if you want to know how many boxes, how many boxes in a subshell, you just take the value of L times 2 plus 1, which that's just your 3, 5, 7, 9, 11. Okay. Okay, so that's how far I wanted to get. And we'll pick up here on Friday.